Welcome to Indium Corporation here at PCIM. I'm delighted to be joined by Joe Hertline. Nice to see you, Joe.
Yeah, it's great to see you, Trevor. Thank you for your time.
Yeah, so we want to talk to you today about a range of things, actually, and I want to start off with the fact that silicon carbide seems to be the material of choice at the moment for a lot of these advanced packaging solutions, and it's moving towards gallium nitride and maybe even one day glass. How do you manage that transition, and what's your view on it?
Yes, I think the key thing for us as a materials provider is really recognizing the different application needs. Certainly silicon carbide, gallium nitride, they're emerging, they're used in various applications, but it's really the end device needs that we're looking at. And our strategy, our goal for that is to have a variety of options available for materials, whether it be die attached materials, thermal interface materials, substrate materials that we can actually offer that meet the application needs. So, for example, within the automotive space, where you have a demand to have more efficiency, extend longer ranges for the vehicles, reduce charging times, we see a lot of performance needs driving to higher junction temperatures, and that's where high-performing materials like sintering, silver sintering would be ideal. But then in other applications, industrial scenarios, where maybe it is manufacturing scalability or volume or even cost is more of a factor, we also can look at offering different materials that scale down to that need.
Okay.
So that's our approach.
That's your approach. So how does all this fit into the heterogeneous integration argument? I mean, do you start off by looking at what the optimum performance metrics might be and then dial back from there to try and fit in with the other range of materials you've got to work with?
Yeah, that's a good question. That's exactly the approach, because really ultimately you need to be able to meet the design requirements. So we're looking at what is the mission profile, what are the operating temperatures, what are the reliability needs of the device. At that point in time, then it really comes down to how do you most efficiently manufacture it. So from a heterogeneous integration standpoint, that's looking at compatibility with different assembly sets, or making sure that the entire assembly is compatible. And we would look at identifying the correct die attached material or the correct thermal interface material, et cetera, to be able to meet those requirements, but then to be able to manufacture it efficiently. So one example could be identifying a soldering alloy that could be processed in a certain temperature range and consolidating those manufacturing steps into a single step. So instead of having multiple steps to do the packaging, you could actually reduce those into a single step. Have a consistent material across all of the entire package, and by definition, the definition of that, you'll have you'll compatibility with the heterogeneous assembly set.
Right, I see. So one example of that might be, for example, the Indalloy materials that you've got behind us here, which have got a lower processing temperature.
Yes.
Tell us a little bit about how that works.
Sure. Yeah. One of the big needs we've seen emerging in the market has been, again, striving to realize performance on the thermal side. So driving higher efficiency out of the power electronics, that increases the overall temperatures and the thermal demands on the system. So again, if we look at this as an entire system and we bring back to the heterogeneous integration standpoint, how do we provide a material that is compatible and can address the needs of the system, but also meet the thermal performance requirements? So when we we're looking at that, we're recognizing a lot of the other assembly materials used in the packaging, the encapsulation materials, those are not designed to withstand high temperatures. So as the temperatures and processing temperatures increase, you start to have a risk of breakdown, mechanical failures, and those type of problems. So when we looked at the big picture, we thought that we recognized the gap in having a product that could be processed in a lower temperature range.
Right.
So in this case, the Indalloy 301, it actually can reduce the soldering temperature range down below 220 C, and that's a critical point because that reduces any of the risk for the encapsulation materials to actually have mechanical failures.
Right.
But at the same time,
so that's the point where they're going to start to break down.
Exactly.
So you want to get it, yeah.
Exactly. So preventing that point where they would break down, and then at the same time ensuring that as an overall system, you're meeting the thermal needs and you're meeting the reliability needs when you look at the overall mission case.
Right. Okay. Interesting. So one of the other areas I want to just touch on while we have you here, Joe, though, is the other interconnection method which you mentioned earlier, which was sintering. At the moment, obviously, sintering is becoming more and more popular, but it uses silver, which is obviously not only one of the best materials, but also one of the most expensive. So, there has been also some people that are working towards using copper as a potential replacement for that. What is the Indium approach to sintering?
Yeah, and again, our key thing is we're recognizing that there's many different application needs. In some cases, silver sintering is critical to realize that performance. But again, in other cases, copper sintering is a viable solution. So here at Indium, we're actually developing copper sintering material solutions, sinter paste that could be applied. Again, using copper as the core material. And again, this could reduce the overall cost of ownership. When we look at it not just from the standpoint of the true discrete material costs, but the overall system costs, that's where we're looking at how we can bring solutions forward. So we have different formulations, some designed to with where pressure needs to be applied, pressure sintering, some that can require just reduced pressure or even no pressure in an extended temperature profile. And the advantage of that is it provides options that can address the different manufacturing concepts that our customers see. And the other advantage of copper is you have a little more flexibility in the overall assembly materials. So you have a little more flexibility with the metallization choices that you choose for the die or for the substrate. And again, it helps with the cost of ownership. We see that as a critical need, so we are advancing our copper sintering materials along with our silver sintering materials.
So what are the trade-offs when you're using a non-pressured sintering process?
Yeah, it really comes down to the overall manufacturing process. So really it comes down to temperature, time, and then just looking at adding some time, adding some temperature to the process to allow you to basically realize that same sintered interface at the end of the process.
So basically just a longer cure.
Yeah,
basically.
that's right. Yep, that's right.
Well, some really interesting information there, Joe. You're always coming out with new innovative materials, and I want to thank you for giving us a quick overview today.
Yes, thank you, Trevor. It's great to be here at PCIM and obviously be part of all this technology innovation. Thank you very much.